Hello, I am Joseph Wright from Drexel University, and this work is titled Finite Element Analysis of Crack Formation within Compacted Powders. The development of defects during compaction has many attributed causes, with particle cohesion being a central theme. In this work, we explore the effect of small cracks implemented within both particulate and continuum models within ABAQUS 2021. Cracks developed closer to the surface of models are seen to have both higher adjacent contact stress, suggesting the crack will propagate, and stress intensity factor, indicating a high concentration of stress at the crack tip. Since compaction forces two or more particles together, we can assume that the development of defects is attributable to the material failing to bond. Insufficient compaction force, lubrication on particles, or contamination within the powder can all prevent bonding between particles. To simply model them, these particle-scale defects can be considered small cracks with the development of tablet or large-scale defects dependent on the location and severity of cracking. We can classify tablet-scale defects as lamination, one or more horizontal cracks forming towards the top or bottom surface, fragmentation, material chipping off the edges where faces meet, and bubble formation. Literature suggests lamination and bubble formation are driven by the presence of air in the compacted powder. We developed a particulate model in ABAQUS 2021 where an array of highly ordered particles were arranged with interparticle pressure. The interparticle pressure was discretized according to single action and double action pressure gradients as developed in Zavaliangos 2017 and Klinzing 2019. Using this approach, we were able to examine the local vertical stress on a contact adjacent to the crack, indicating a crack's propensity to grow and disturb the adjacent contact. We compared the ratio of the top crack adjacent S22 and the middle crack adjacent S22 and found the single action profile developed a ratio greater than 1 for all compact heights, while the double action profile remained under 1. This indicates the propensity of defects to develop at certain heights is heavily dependent on the location of the maximum interstitial air pressure as well as the magnitude of the pressure. We also developed a continuum model in ABAQUS using a crack engineering feature instituted within a bulk solid. Using the stress intensity factor evaluated about the crack tip, the stress concentration was examined, and we can obtain a geometry factor for this system. In these models, we developed a crack in a bulk solid with a variable total height until the geometry factor showed very little change with increased crack to surface distance. Then, the bulk height was set to double that minimum interaction distance, with the crack position moving up toward the top surface. The geometry factor is plotted in the bottom plot for the variable and fixed cases, and the deflection of the top surface can be observed in the figures. In the two models, we examined a particulate model with discretized interstitial pressures and the development of a large crack in an axisymmetric high aspect ratio compact, representing entrapped air and lamination respectively. Though the particulate model is highly ordered with discretized pressures and has octagonal particles, these assumptions aid in computational efficiency for enhancing our understanding of the interplay between porous media and the pressure gradients driving air effects in powder. The continuum model assumptions include the axisymmetric high aspect ratio compact with a single defect forming. Both models utilized elastic materials. Future work in this area could include merging air pressure effects with the continuum model and comparison of defect formation methods for models. Developing a crack engineering feature in the periodic model would allow direct comparison of stress intensity factors between the two models. This work was funded by a grant from the Manufacturing PA Innovation Program, and attendance at PowderMet2022 and AMPM2022 was made possible by the MPIF NSF student grant. For more details on this work, please come see our presentation titled Development of Air-Induced Defects Within Powder Compaction at 3:35 p.m. on Monday in the PM21 Compaction and Forming track. While this poster focuses on the specific method of crack formation within finite element powder models, the presentation focuses on the development of air within powders and the effects it has in compaction. We explore additional finite element models using pressurized cavities and their effects on the compact. If you are unable to attend, please explore our paper in the conference proceedings on the same topic.